alternating series. If we looked at the harmonic series, we know that that series diverges. What if we looked at what is called the alternate harmonic series? How is this different? We can see that this has this -1 to the n plus 1, and so if we used n equal 1, we'd get -1 to an even power, which is positive, and then each successive term will alternate signs because the odd powers will be negative, the even powers will be positive. So it looks like this, and we have our, it looks like our harmonic but alternating signs here. So the question is, does this one diverge as well, or does this one converge? Let's look at some of the partial sums here so we can kind of see what's going on here. We see s sub 1 is 1. Adding 2 of those we get 1/2. Adding 3 terms we get 5/6. Adding 4 terms we get 7/12, and so forth. So is this converging? Let's look at a graph, and as we look at the graph, it appears to converge about this line here, because we started here at 1 and then we have these back and forth, but it looks like we are converging here. So we're going to be interested in an alternating series test to determine if alternating series converge or not. So if we have a series and it comes from having some series but putting this factor in, this -1 to the n minus 1, or it could be to n plus 1 to some power of n here, and it could even be to n, different ways to list them. So they could either start out positive or negative, but they will alternate signs because of this, because we're having b be a positive number, so these will alternate signs. It is called an alternating series, and we want an alternating series test then, and here it is. If this alternating series, so we have b sub n being positive, and then we're going to have this alternate because of this power here of a -1. If it satisfies these two conditions, then it converges. So what are the conditions? First of all, if any term is less than or equal to the term in front. Now we're not considering the positive or negative, just the b sub n part. So any term is less than or equal to the term in front, and if these terms, the limit as n goes to infinity, these terms is 0. So these terms need to go to 0, then the series is convergent. So let's first see if we can visualize what this means. So we start here and we add the first term, and we have the first partial sum s sub 1. And then we take the second term b sub 2, and because that alternating, we will subtract that. But remember that any term is less than or equal to the term in front, and so then we add one that's as they're getting smaller, equal to or smaller, and then we subtract the next one, then we add the next one, then we subtract the next one, and you can see as we do this that we appear to be narrowing in on some limiting sum. So let's look at this just a little bit closer. So as we take this, we are going to start by taking the first partial sum, which is b sub 1, and then as we take b sub 2, we will subtract this positive number, and so we will be decreasing here, and we have this s sub 2. Then b sub 3 we will be adding, then we'll be subtracting. We're going to continue this pattern, and here we will look at the b to the n plus 1 term that we added. Well, as we look at these partial sums, let's look first of all, since these terms are less than or equal to the term in front, the even terms of the partial sums form an increasing sequence bounded above by S1. So here we see these even terms, and we can see that that would be increasing, and it would be bounded above by S sub 1. And the odd terms will be decreasing, and they will be bounded below by S sub 2. So what do we have here? We have a bounded monotonic subsequence of these partial sums. So they will have a limit. They will converge. So let's let the limit be L sub 1 for our even numbered terms, and let it be L sub 2 for our odd terms. If we have the sum of the 2n term, that's going to be the sum of the 2n minus 1 term plus the b to the 2n term, because we just be adding on one term to get this new sum. Now let's take the limits of all of those. Well, but we know that these two limits are L1 and L2, But looking here, our second condition was that the limit as n goes to infinity of b sub n equals 0. So this is going to go to 0, and that tells us that these two limits will equal each other. So L1 equals L2, and then we can just simply call that L. So they will be converging to that same value of L, and therefore this sequence does converge. So if we go back and look at the alternating harmonic series, it satisfies our two conditions because we see that any term is less than the term in front of it, because this will always be true. And we see that these terms, if we take the limit of this, it is going to 0. So the alternating harmonic series does converge by the alternating series test. Let's go ahead and just look and see. This is what the terms themselves look like, and this is what the sum, the partial sums, look like. And we can see that these do go to 0, and we can see these do converge to a finite value. That finite value happens to be the natural log of 2. For most series that we'll be interested in, we will easily have this first condition. So when that's met, then we just need to show that the terms go to 0 for the alternating series test. So as long as we know that we have these terms decreasing, we just worry about, is it going to 0? So now that we're saying, okay, as long as the limit as n goes to infinity of b sub n equals 0, we have a convergent sequence, we've got to be very careful, because if the series were positive terms and we knew it went to 0, it does not imply convergence. Remember, we know nothing. However, if it's an alternating series, as we showed here, if it goes to 0, it does imply convergence. So we have to be careful that we don't apply something when we have positive terms, but when we have alternating series, this will give us convergence.